Okay, I think we're alive. And hello and welcome everyone to the latest episode of the AI co-learning program. I'm your host Bruce, and it's a pleasure to have you join us again. In this session, we're diving into a topic that's pushing the boundaries of both AI and scientific discovery, how AI is reshaping scientific research. As scientific challenges grow increasingly complex, AI is becoming an essential partner in accelerate models, uncovering patterns, and even formulating new theories. So today we'll explore the integration of AI for science, symbolic regression, and reinforcement learning, and how they're going to open new pathways for innovation. And we're truly honored to have with us Dr. Yuan Tian, a postdoctoral researcher from ETH Zurich, whose work sits at the intersection of AI and scientific exploration. And he's here today to share not only theoretical insights, but also practical applications and results from his latest work. So whether you are a researcher, developer, or just simply curious about where AI is heading next, you're in for a treat. So hi, Dr. Tian. Thank you for joining the co-learning series. Now the floor is all yours.
Oh, okay. Thanks, Bruce. And hi, everyone. My name is Yuan, a machine learning researcher. I did my PhD and postdoc at ETH Zurich, and today I'm gonna present my work on AI for science, named Interactive Symbolic Regression with Co-Design Mechanism through Offline Reinforcement Learning, which published on Nature Communications. And so let's start. AI for science. We are living in a revolutionary time. Artificial intelligence is emerging as a fourth paradigm of scientific research and scientific discovery. After experimentation, theory, computation, and now AI and data analytics are adding a new transformative layer to how we discover knowledge. Below the timeline are icons for material science, life science, and astrophysics. Each represents how AI accelerates discovery in fields. For example, AI can predict molecular structures to design new materials, analyze genetic sequence in biology, or mine telescope data to find astrophysics law. The core challenge is that all these domains, scientists face the task of discovering the underlying mathematical equations that govern natural phenomena, rather than just fitting parameters to a known formula. We want AI to discover the formulas themselves from raw data. This is exactly symbolic regression does, and it is the mission of our work. Now, to tackle this problem, let's first understand what symbolic regression is and why it is useful. Symbolic regression is a form of regression where the goal is to find the formula itself, not just fitting coefficients to a fixed model or or the weights of neural network. For example, in traditional regression, you might assume the model, for example, y equal to ax plus bx plus c, and only solve for abc. You are getting parameters, but symbolic regression says we don't even know the equation form. Given data points, it will search over mathematical expressions to find the best formula that explains the data. It's like letting the data itself decide if the relationship is quadratic, sine, cosine, or something else. For instance, imagine our data follow the underlying truth follow y equal to 0.5x squared minus x plus 1, but the algorithm doesn't know that formula. We give the raw points here. The symbolic regression algorithm will try candidate term like x squared, sine x, and so on, and eventually discover symbolic regression, discover at its best fits. Notice the animation. As the algorithm runs, it shows data points, and our algorithm tries and discovers the formula. The core value of symbolic regression is discovering concise, interpretable, unknown nodes. Unlike black box neural networks, which might say the model predicts 0.87 with no explanation, symbolic regression produces human readable formulas like y equals to like this, and which can directly deriving new physical laws from data, like an AI Newton discovering motion laws, building interpretable models in finance, healthcare, where transparency is the key, and understanding complex systems in concise equations. Finally, scientists can uncover new materials or biology mechanism, and the industries can optimize process with formula from formula insights. In short, symbolic regressions turns data into human readable formulas that can revolutionize understanding and decision making. Historically, symbolic regression has been tackled by a couple of methods. Let's review two major approaches and their limitations. One classic approach is genetic programming, which simulates biology evolution to evolve a formula. Think of it as Darwin nature selection for equations. We start by initialization a population of random formulas. And like this. And for example, we might start with formula like x plus 1 sine x, or 2 times x squared. We evaluate each, then select the best one. When we do crossover, we might combine x plus 1 and 2 times x in some way, and the mutation means might take x plus 1 and randomly change to sine x plus 1. And here is the animation. When I click the button, the model will run through more generation, and you will see better formulation emerging. Genetic programming has been used successfully in many domains, but it has significant drawbacks. The search space of possible formulas is astronomical. For example, even with just 10 operators, 5 variables or constants, and formula length of 5 to 20 symbols, the number of combinations is on the order of hundreds or more. That means random mutations are like buying lottery tickets. You have to do many generations to even stumble upon good formulas. And another big issue is integrating prior scientific knowledge. If research knows the result might involve a sign function, the genetic programming approaches doesn't have any easy way to bias the search toward to sine x. Also, there are some other problems: the bloat, the computational cost, and the local optimal. The second method is autoregressive transformer, which borrow the idea from NLP. Here we treat the symbolic regression as if it were a language translation problem. The input language represents the data points, the observation, and the transformer is the neural model in the middle, and the output language is a mathematical expression. So just like translating English to French, the transformer can translate data patterns into an equation. In practice, we encode the data set into some learned data fingerprints and then decode it, token by token into a formula. This approach has many advantages. For example, powerful learning, it leverages deep learning, the neural network on large data sets, and faster generation compared with the genetic programming, which is time consuming. And once the transformer-based model trained, it can output formula quickly. And also it's generalized well. It can learn structured pattern from its training example. Transformer do bring speed and power, but there are also have specific challenges. First one is the exposure bias. All transformer model, even the language model or large model for foundation model for time series, because during training, the model always see the correct private symbol by teacher force training mechanism. But during inference, it only seeing its own prediction. This mismatch means small early mistake can cascade into completely wrong formula. Also, it's still difficult to integrate prior knowledge. We can try to give hints like prompt to a transformer, but it may not reliable follow them. For example, if we say include a sine function, the model might ignore it or wrongly use cosine x. There is no straightforward way to enforce domain knowledge. In short, transformer offers speed, but they struggle with reliability and incorporating expert insights. All these shortcomings of transformer and genetic programming suggest we need a more robust, controllable approach that can leverage both data and human expertise. Now that we motivated the need for better methods, let's switch gears and introduce some reinforcement learning concepts, since our solution use reinforcement learning. Let's skip some slides. To build intuition, think of reinforcement learning like training a dog from the simplest way to understand. The core idea is learning by trial and error with reward. Here, dog is the agent. The owner's commands, its states, and the dog's choice are actions. If the dog does the right action, it gets a reward. Over many trials, the dog learns a policy, a strategy mapping command to actions to maximize the treats. Here is also an animation, like if the owner says sit and the dog choose bark or roll, there is no reward, only the sit. So basically it's learning by trial and error. So and here we can map the knowledge to formula discovery from this animation. Building a formula is a training, and the state's gonna be the current partial equation and plus the data feature, the observed data, and the action is add an operator or variables to the partial formula or finish it. And the reward is gonna be how well the formula fits the data. And the policy is the strategy to building good formulas from partial pieces. So just as the dogs learn the best action to get treats, our agent, this work will learn which formula building actions leads to high rewards. Let's briefly review reinforcement learning's revolution. It starts with Bellman's work in 1950s on dynamic programming and the Bellman equations, the mathematical foundation of optimal decision-making. In 1989, Q-learning was introduced, a model-free control method where an agent learns the value by actions by experience without knowing the environment dynamics ahead of time. This was a breaking through because it let agents learn optimal actions purely from trial and error without any model knowledge. And fast forward to the 2015, the DQ and DeepQ network introduced by OpenAI, deep neural nets were combined with Q-learning to play Atari games at human level. This ignites the deep reinforcement learning era, and in 2016, AlphaGo used deep reinforcement learning plus Monte Carlo tree search to defeat the world champion at Go, a game once thought unsolvable by AI. Finally, in 2019, OpenAI 5 achieved world champion level at Dota 2, a complex multi-agent game with partial observability. We're gonna talk more on these two cases later. So, just some understanding of the very basic mathematical foundations of reinforcement learning. Reinforcement learning is grounded in Markov decision process framework, and the agent's environment loop diagram, the agent take actions, the environment responds the new state, the state next, and receive a reward. The goal is to learn an optimal policy pi star that maximize some measures of cumulative reward. And there is some basic idea like how reinforcement learning works. There is expected return, which capture the idea that immediate rewards count more, but we still care about the future. And the Bellman optimality for Q values, this says the optimal Q value of taking action A in state S equals the expected immediate rewards R plus a discounted best future value from the next state. And here is the Q learning update. So let's quickly skip this the theory part, boring theory part, and to the the two success games. So on the left, AlphaGo, the first AI to beat top human Go player, and Go has enormous search space, and they won by combining deep neural networks with Monte Carlo tree search and massive self-play. And this work demonstrates deep reinforcement learning solving what was once thought unsolvable tasks. And on the right, OpenAI 5 and reinforcement learning system that learn to play 5 vs 5 Dota 2 games at professional level. Dota is a continuous action space, partially observable game with thousands of actions, which is way more harder than Go. And still, the reinforcement learning agent beats the professional AI, the human team, and its innovation includes training a team of agents in self-play on massive scales. So these two examples highlight that reinforcement learning can handle vast search space and high-dimensional decision problems. The lesson for us, both Go and Dota have enormous action space like our formula space, and deep neural network with reinforcement learning can approximate complex strategies, and self-play can generate more training data. We plan to leverage this same principle for discovering formula. Now, with reinforcement learning potential in mind, let's see how we build our solution. The ThemeQ is our framework that treats symbolic regression as a sequential decision-making game. The core idea is an AI play a game of building a formula step by step, like a scientist drafting an equation. Each move it makes is adding an operator or variable to the current partial expression. We use Q-learning, so the AI knows which move tend to yield good fit. And the key advantage, we have emphasized 3 points. First, the intelligent search. This replaces the blind search of genetic programming with direct exploration. Instead of random guesses, the agent learns Q and much speeding up the search, and it can easily integrate expert knowledge. Humans can intervene at any point to guide the search. The framework naturally allows incorporating with domain knowledge. I'm gonna show you some case later, and flexibility. The method can easily extend to more complex problem space. For example, we could include actions for taking derivative or integral if needed. Here is an example. Constructing an equation is really an incremental sequential process, and you can see here every step the agents, the bubble here, the agent can reasoning. For example, here the data seems to have a linear trend and periodic fluctuation, and start with a plus operator, because plus operator gonna have it's a binary operator, gonna have more decision later. And next step, so it first do an x, the linear part look like the y equal to x, and let's add that to the left branch, and then it decides the right branch for the fluctuation, probably a cosine term, and finally it's we use the placed the x to fill the placeholder and done. So this is how it works. So why sequential decision making? Because constructing an equation really is an incremental sequential process, just as scientists build and test parts of the hypothesis. Our agent builds and tests parts of a formula by using reinforcement learning agent. It learns from experiments, which building strategy work. The bottom two bullet it says a natural process equation are built incrementally, and the agent learn from experience which sequence of actions works best for different type of data. And this sequential framing justify our approach over one-shot model like the transformer-based model. So next, to make the learning more efficient, we employ offline reinforcement learning. In standard online offline reinforcement learning, an agent learns by interaction by itself, trying random actions and seeing the results. For symbolic regression, that means the agent would have to propose thousands of random partial formulas, check each, and get reward. It's very inefficient. Instead, we use offline reinforcement learning. It's like a student study an expert's textbook. We train from a fixed data set of high quality expert trajectories, example, sequence of steps that lead to good formulas. And offline reinforcement learning, it's like a chess player studying grandmaster games. The AI learn from proven strategy with no trial and error needed, which is very suitable for this kind of sparse reward tasks. And it learns much faster and generalize also well. And it's like learning from thousands of solved examples. A key part of our offline approach is using the conservative Q-learning to ensure the robustness. In offline reinforcement learning, a big risk is overestimation. The agent might get overly optimistic about actions it's never actually seen, because it's always seen the success actions, and for other actions it cannot try them and get feedback. With the conservative Q-learning, we mitigate this. The agent stick to what it knows. If it sees sign X works well, it learns to stick to the known good strategy, so cosine won't be overvalued without evidence. In practice, we add a penalty in the Q-learning loss to push down the Q value of out of dataset actions. The result is that the learned policy, after using the conservative Q-learning, the policy doesn't choose widely risk actions. And the key benefit is it's much more robustness, generalization, and can reduce the risk and no environment interaction needed. It's pure offline and can much speed up the training process. So we have built up a lot of pieces. Let's look at the big picture of the SimQ architecture. This slide shows SimQ entire decision loop. So below here, we can play the flow animation. How the SimQ works. So first, the agent observe the current state. One part is the data points and one part is the current expression tree. And both of the data points gonna send into the data encoder, the points encoder, and the tree gonna send to the tree encoder. And we combine these two extracted features. We understand the data fingerprint and partial formular fingerprint, which is latent under the latent space, and we fuse the information and feed to the decision brain. And our Q network training by the conservative Q learning will gonna output the value score for all possible actions. In our case, we have 30 different actions contains different operators, parameters, and constant. And here is the visualization. Gonna visualize before we visualize the thought bubble, how the agents may reasoning. Here from the neural network itself, from value perspective, we can see how it works. So in summary, you will see the agent adding parts one by one, and each step showing the partial equations and the Q value indicating which action it thinks are best. And here is some other case, also example. It observe it and choose actions, place the actions, and loop over again. So then we evaluate SimQ on a standard public dataset. It's called SSDNC. We achieve state-of-art performance in both recovery rate and the goodness of fit. So compare with all the other state-of-art methods like the symbolic GPT, NeSimRes, and the TJSL. We are on this dataset. We are the best, and from both the recovery rate means the skeleton is recovered and the fitness of the point itself. And what this result means, the scientists can trust symbolic or the SimQ to find accurate mathematical models for their data. And the reinforcement learning approach successfully address the limitation of prior risk methods. All these prior risk methods are trained by transformer, like the autoregressive manner, and strong foundation for extending to more complex mathematical structures. Next, we check some real-world scenarios, like the drift terms. So using we talk about how to integrate the prior knowledge, and in real world scenario, like a lot of physical scenarios, like there gonna be a base law. However, when we're doing the experiments, there probably have some oscillations. So we need to find out what exactly the drift term is. And so we can input the base law, the prior knowledge to the SimQ, and let the SimQ, our SimQ agent to complete the drift part like this. For example, here we know part of the law y equal to x squares, and we see the red points showing a periodic oscillation around that parabola. And we suspect there is an extra term, perhaps something like plus sine x, and SimQ starting with the lower part of the equation, and the agent treats the known component as given the partial experiment tree and attempt to add whatever improve the fitness. And finally, after a few steps, SimQ can identify the best drift parts that explains the drift. So we can see that it's very flexible and the efficiency, and human in the loop, the scientists can guide the search with their domain expertise. So this feature is especially useful in scientific discovery, where some base model is known and only an additional effect need to be determined. And this is all, the last slide is the most exciting feature of our methods. An expert can interval in any stage in the symbolic regression process and providing hints or correlation to guide it in the right direction, significantly boosts efficiency for complex problem. There is another case. Without any hints, let's SimQ find the formula on its own. Like this shows the baseline performance. It's like this. It's might not be perfect or optimal. So after real human experts involved, after observing the round one results, we notice that something can be provided. For example, the formula parts f and pi1 term might be an inversely related, and we feed SimQ this hint. Let's the SimQ run second. We can see the results improved significantly. So this is how the co-design works. How the works. So in the end, the applications, the symbolic, our model is right now open source, and it can be applied to physics, astronomy, materials, chemistry, biology, medicine, finance, and operations, also robotics and anomaly and software system. The conclusion, so our SimQ frameworks model symbolic regression as a sequential decision-making problem and solved with offline reinforced learning, and introducing an innovative human AI in the loop mechanism. It offers a powerful, flexible, and interpretable new paradigm for discovering scientific law from data. And the key contribution is beyond blind search and embracing expert knowledge, and with huge potential. So that's all, and you can check the papers and view the projects on the GitHub. So thank you, and I'm ready for any questions.
Yeah, thank you, Dr. Tian, for the inspiring talk. We're now open the floor for questions from the audience. Please drop your questions in the live chat. Okay, let's see. So the first question we have here is, where do you think AI has the greatest potential for breakthroughs in scientific research? And is it in accelerating experiments or discovering new scientific laws or providing new tools for some interdisciplinary work?
So, if I understand correctly,
Mm-hmm.
you are asking which fields may most potential to apply SimQ, right?
Yes.
Um, from my perspective, I think physics and finance is the most promising field because actually I have tried to use symbolic regression to find some alpha factors to guide trading, and it's the most and it works very well, but it fits it finds the underlying law of the return and the risk, but it's not the only advantage. The most exciting part, I think, it's symbolic regression compared with other machine learning models. It's because we are pre-trained, so you don't need to train it, and you can only give the model 50 data
Mm-hmm.
points, which is much more less than training a machine learning or deep learning model. So with few data, you can have a roughly good the roughly good model which is interpretable. And so basically you can do high frequency treat. And so I think it's promising. And
Okay.
also for physics, it's quite straightforward because like the drift term part, you always face some problem that the textbook equations do not match the reality because there
Mm-hmm.
is some disturbance, and you can use symbolic regression to find the underlying disturbance, which is very good for modeling model dynamics and dynamics modeling and doing optimization. So yeah, physics and finance, I think it's the best way to try it.
Okay, I see. Uh, let's see the second question. Yeah, the second question is symbolic regression shows great promise in discovery formulas, but the search space is often enormous. So, what do you
Yeah.
see as a key breakthroughs in this area going forward?
So it's true that we mentioned multiple times that the search space is huge. This is also the reason why we use offline reinforcement learning, and some
Mm-hmm.
others may use supervised learning. I think it's quite straightforward. For example, playing the AlphaGo, the first version of AlphaGo, have two training stage. The first stage is supervised training. It learns the master the textbook how to play Go. After this, it has many understanding. It do the self play. So in our case, I think offline reinforcement learning or supervised learning is a necessary pre-train part, pre-train stage to give the agent, to give the model necessary understanding of the math, of the physics, of the data points, of the expressions. And after that, the when it faces some new tasks and it can not immediately give you a good result, you can use online search. Reinforcement learning is also born for search. So SimQ it's we pre-train it, but it's also support online search because with the pre-trained knowledge, the online search space is much more smaller because it won't do the unmeaningful search, and this can decrease the search space. Yeah, thanks.
Okay. So the third question is, when applying reinforcement learning to symbolic regression, do you think it's great its greatest value lies in exploring formula structures or in optimizing search strategies.
I think it's really a good question. So let's talk about both parts. So
Mm-hmm.
first, exploring formula structures. Um, Actually, I think exploring formula structures and optimizing search strategies is very similar. I don't know exploring formula structure means structural exploring. If we talk about structural exploring, it's a hot topic in the whole reinforcement learning research field because reinforcement learning is the largest difference between reinforcement learning and supervised training is supervised learning is reinforcement learning required to explore, and we always want the agent to have a structural exploring because we don't want the agents randomly exploring. And it's a good question, and I think it's also a good way to for the next step. For example, we can use Monte Carlo tree search to explore formula structures. And the second part is optimizing searching strategy. To be honest, I really think there is no all. It's talk about the same thing. I think exploring formula structure is the same as optimizing search strategy. I think it's the same.
Okay. Yeah, I think that's pretty much everything. Every question for the lecture. Yeah. So thanks again to Dr. Tian for sharing his expertise on AI for scientific research, and we'll share the replay and slides through our community channels. Please stay tuned for our upcoming sessions. And until next time, keep questioning and keep co-learning with us. Thank you. And bye, Dr. Tian.
Bye. Thanks. Thank you. Have a good day.
You too.